This presentation will be a brief introduction to resistors and Ohm's law. Matter is made up of particles. Some particles have a property known as electric charge. We'll mainly talk about electrons and protons. Charge comes in two varieties, positive and negative. Protons have a positive charge, while electrons have a negative charge. And these charges are equal and opposite, so that if they combine, a proton and electron combined would have a neutral or zero electric charge. The charge comes in a unit known as a Coulomb, named after Charles Augustin de Coulomb. We'll find that the Coulomb is a rather large amount of charge, I'll say an industrial amount of charge. For instance, to express the charge of a proton, we will need scientific notation. It's 1.602 times 10 to the minus 19 coulombs. While many situations are neutral, have a net zero electric charge, a small amount of charge can build up in some situations. A common one is sort of on a winter day in a carpeted room, then some charge might build up. The charge is most noticeable when it moves, when it gives you a shock or an electrostatic discharge, ESD. The stored charges rapidly move from one place to another, usually to neutralize. Now, it might be slightly annoying for you to get a shock, but if you were to open a computer and be working on its circuit boards, that ESD can cause quite a bit of damage. When charges are moving, then we have a current. Specifically, the current is the rate of charge flowing past a point, the amount of charge going by per second. It might be a discharge, a sudden change in the charge, a sudden movement. It may be a direct current, DC, a sort of steady movement in one direction. Or an alternating current, AC, a sort of constant back and forth motion of changing the direction. The current comes in a unit known as an ampere, which is a coulomb per second, and that unit is named after André-Marie Ampere. The currents in computers are often smaller than an ampere, and so we will have to get used to units like milliamperes. And finally, currents are measured by an instrument known as an ammeter. The diagram shown here shows an ammeter that is in series with a resistor. So the alternating long and short lines that have a 6V, 6 volts next to them, that represents a battery. And we think of positive charges as coming out of the side of the battery with the long end and going around a circuit, a closed loop, and ending up on the side of the battery with the shorter end. The charges then pass through the first object, the sort of zigzag line marked R1, which represents a resistor. And after they've gone through the resistor, then they go through the ammeter. And we're just discussing here what is meant by series. And since all the current that goes through R1 must also go through the ammeter, then the resistor and the ammeter are said to be in series. See the same current. So we talked about the current flowing from one side of the battery, the long end of the battery, toward the short end of the battery. In other words, current has a direction. By convention, the direction of the current is the direction in which the positive charges flow. These conventions of the signs of charges and the signs of currents were established mainly by Benjamin Franklin before we knew what was going on at the atomic level. This has led to the sometimes confusing situation that what is often happening is that there are negative charges flowing, and then they flow in the opposite direction to the current because the electrons have a negative charge. So when we have a battery in a circuit, it's often sitting there waiting for us to ask it to do its job. In other words, it has some potential energy. It has the ability to do some work. It's not always doing that work, but it has the ability to do that work when called upon. A simple example of work in physics may be lifting a weight, or in general moving something, maybe like charges around in a circuit. So certain arrangements of charges, like those in a battery, have potential energy. Actually, what's more important is the difference in potential energy. So there will be an arrangement of charges in the charged battery and a different arrangement of charges in the drained battery. And so it's that sort of rearrangement that allows the battery to sort of give up its energy to something else when we want it to do the work. And energy comes in a unit known as a joule, named after James Prescott Joule. And so we're interested in the energy in arrangement of charges, and it stands that the greater the number of charges, the greater the energy. And thus it's convenient to define a potential energy per charge, and this is the electric potential. And as we said before, what was really important was the difference in potential energies. So in this case also, it is the difference in the electric potentials that's important. So we have the potential difference, and this is another term for the voltage. And so it is the potential energy per charge, the difference in the potential energy per charge between two charge arrangements. This comes in volts. And since it's energy per charge, it is a unit of joules per Coulomb, or J divided by C. And this term is, again, a volt, and is named after Alessandro Volta. And now we see our sort of common unit that we know that describes a battery. And finally, the instrument that will measure a voltage is a voltmeter. So again, a battery is characterized by its voltage. It has arrangement of charges that have an energy. Because it's charges that are causing that energy, or that energy change when they rearrange, it is convenient to define an energy per charge, or a joule per Coulomb, and that gives us our unit of volt as the sort of unit describing a battery. This diagram shows how a voltmeter will be connected in a circuit. So we have the 6-volt battery V1, and it sends out positive charges out of the top, the long end, and those charges go through R1 and then go through R2 until they get to return to the short end of the battery. We see also that we have a voltmeter, and there's a connection of wire. The red is representing wire. There's a connection of wire on the top side of the resistor R2 and the voltmeter. And there is another wire that connects the bottoms. And when you have a connection on one side of a wire and a connection on the other side of a wire, then the two objects are said to be in parallel. So the resistor R2 and the voltmeter are in parallel. So within the battery, there is an arrangement of charges, and those charges cannot rearrange on their own, hence the energy is stored in the battery. But when the battery is connected to, say, a light bulb in this case, then we have made a path from one side of the battery to the other. This allows those charges to rearrange, allows the battery to give up its energy, and so it, 1, causes a current, and 2, gives up its energy so that that current can do some work, say light the light bulb. So we attach our battery, which is characterized by a voltage, to some device like a light bulb, and that gives rise to a current, which is measured in amperes. And this brings us to our next quantity of interest, the resistance. The resistance is the ratio of the voltage to the current. So the voltage, again, was associated with work or energy, and so the resistance tells us whether it's going to take a lot of work to get the current going, that would be a high resistance, or just a little bit of work to get some current moving, that would be a low resistance. The unit of resistance is known as an ohm, named after Georg Simon Ohm, and it can be measured by a device known as an ohmmeter. This picture shows us using a multimeter that has been set up as an ohmmeter. As opposed to when we measured the voltage with a voltmeter, and when we measured the current with an ammeter, in both of those cases, there was a battery supplying some energy. In the case of measuring resistance with an ohmmeter, we do not want a battery in the circuit. So we remove any battery from the circuit, leaving only a resistor or resistors, and then use the connect the ohmmeter across that combination of resistors. Having defined resistance allows us to make the distinction between conductors and insulators. Materials in which it's easy to produce a current, that is, materials with a low resistance, are known as conductors. Examples would be copper, gold, silver, and these we use sort of as wires to easily move current around from place to place within a circuit. If a material has a high resistance, then it is difficult to produce a current in there, and we use these materials as insulators to sort of be like a stopping point to sort of not allow current past. Lying between the materials that serve as good conductors and those that serve as insulators, we have materials with sort of in-between behavior, what we call semiconductors. They're not terribly good conductors, but they're not terribly good insulators either. Examples of these would be silicon and germanium. Some semiconductors, however, can be controlled through a process called doping, and we can change their resistance properties significantly. And this makes them very useful, and we will be able to manipulate this property and make devices such as diodes and transistors. But before we get to complicated devices such as transistors and diodes, we want to study simpler devices known as resistors. And towards that end, we introduce Ohm's law. Now, previously we said that the resistance was a proportion of voltage to current. In general, this is not fixed, but there are certain classes of materials for which it is. And these are the ones that are described by Ohm's law. Ohm's law says that the current produced by a voltage is directly proportional to that voltage. Therefore, if you doubled the voltage, you would double the current. If you tripled the voltage, you would triple the current, and so on. Again, this is not the case for all devices, but it is for the devices that obey what we call Ohm's law, and those materials are what we will use to make resistors. So if we showed it in a graph where we were controlling the voltage and the current was proportional, then in the graph we would see a straight line. And the resistance would be related to the slope, and the slope would be constant no matter what the voltage would be. We keep seeing the same resistance. So this proportionality between voltage and current can be written as V equals IR, and this is known as Ohm's law. Now this looks a lot like the definition of resistance that we gave earlier, but it's important to understand that in Ohm's law, the resistance is fixed. So there's a definition of resistance, voltage over current, and that can change. As the voltage changes, the resistance might change. But in Ohm's law, it does not change, and that is the distinction. So we have to be careful with this word law within Ohm's law. It's not something that's always true. Ohm's law is an empirical observation. We will take a material, we will apply voltages to it, we will see if the current corresponding to those voltages give us a nice proportionality, then that material will obey Ohm's law, and then we will call it ohmic. But this law, again, be careful about the word law, is not always true. Diodes and transistors, for instance, will not be ohmic. They do not obey Ohm's law. If we have a device that obeys Ohm's law, is ohmic, and its sole purpose is to provide that resistance within the context of the circuit, then that device is known as a resistor. They take up some of the voltage and limit the current that other devices within the same circuit might see, so they have an important role. So Ohm's law is a simple relationship between the voltage, the current, and the resistance. And if we know any two of the quantities, we can find the third. For instance, if a light bulb has a resistance of 240 ohms, then we can ask how much current is flowing through the bulb when it is connected to a 120 volt source. So the 120 is a voltage, we'll put it in for V. The resistance, the 240 is a resistance, we put it in for R, and we can solve for the remaining quantity, I. We divide both sides by 240 and get that I is a half. Now let's look at the units. We divided 120 volts, so the voltage came in volts, and we're dividing by ohms, resistance, and so we have volts over ohms, which are amps, and so our answer was 0.5 amp.